Hello.
Hi.
Before we start, hi. Is somehow I couldn't access the so um, so shall we start?
Yeah.
Okay. So welcome everybody to the All Thing Hydrogen webinar. This is one of the series of the webinar under the aegis of the High One. Today, Dr. Vinith Ramlingam, who is going to present and speak about the solar-driven energy conversion and his own experience and research about it. Dr. Vinith Ramlingam is Chancellor's Fellow at the School of Engineering, and he completed his PhD from the SRM Institute of Science and Technology, India. After that, he completed his fellowship under Marie Curie Co-Fund program at University of South Clyde, and also completed his postdoctoral research fellowship at the King Abdullah University of Science and Technology, Saudi Arabia. He's mainly focusing on the development of the innovative catalyst material and device for the solar-driven energy conversion. We all need green hydrogen, and I think Dr. Ramalingam can help there. And it includes the application in green hydrogen and ammonia production or carbon conversion to sustainable fuel like methane or any chemical feedstocks, which could be a source of energy. So without further ado, I will let Dr. Ramalingam to start his presentation, and we should benefit from that.
Thanks, Ketan, for your introduction. Let me share my slides. Can you see the slides? Ketan, you are mute. Can you see the slides?
Yeah, I can see the flow.
Well, thanks, Ketan, for your kind introduction, and good afternoon, everyone. And today I'm going to talk about the photoelectrochemical cells for solar hydrogen production. Particularly, I would like to focus more on catalyst materials and devices. Here is an overview of my presentation today. And today I would like to start with the general introduction about the energy supply and energy demand. And then I move on to what are the various sustainable routes to produce solar hydrogen. And then I will discuss different types of solar hydrogen system. There are three major technologies, which is photocatalytic, photoelectrochemical, and photovoltaic coupled electrolysis process. And then I move on to specifically why photoelectrochemical hydrogen productions starts from the fundamentals of PEC process to different types of PEC systems and what are the material challenges that affects the performance. And then I will discuss more about what are the strategies to enhance the PEC performance. That includes microstructure and nanostructure engineering of photoelectrodes and the band structure tuning and the integration of production layers and co-catalyst materials and bias-free photoelectrochemical systems. And finally, I'll come with the conclusions and the outlook. Here you can see the electricity production by various sources, and it is clear to see most of the energy comes from coal and gas. But what we are here interested is renewable energy resources, particularly the solar energy. Over the last few decades, you can clearly see the electricity produced by solar energy has increased a lot. So I believe there are a lot of potential with the solar energy that we can meet the future energy demand by utilizing this source. So as we all know, energy demands are increasing rapidly due to the increase in human population and energy consumption. If you look at the average energy use in 2011, it was around 13.4 terawatt. And then it has increased up to 18 terawatt in the year of 2012. And the predicted energy needs by 2050 will be around 27 terawatt, which clearly shows that the energy demands are increasing a lot over the years. So we need to find a solution to meet this demand. And The renewable energy resources are one of the major energy resources that can help us to um, meet this demand. If you look at the river hydroelectric all over the world, which is 7 terawatt, and we don't want to put the dam every river to take that energy, but we can utilize some part of this energy that can help us to meet the energy needs. And then again, biomass, which is 7 terawatt. Again, we don't want to use all the biomass that animals wants to eat, so we can use some part of this energy. And then the geothermal, which is 44 terawatt, which is this is one of the major energy resources where we can get from the heat that comes from the Earth's surface. And the another major resource is wind, which is close to 72 terawatt. Again, we can't utilize all this energy, but we can utilize some part of the energy for our need. Finally, we have solar, which is 85,000 terawatt energy, which is basically like 80,000 terajoules per second is striking Earth every day, which is a lot. So if we can carefully utilize some fraction of the solar energy, we can easily meet our future energy demand. For example, let's say if we can able to utilize 0.06% of solar energy, which is close to 50 terawatt, that's what we are going to need by the end of this century. So solar has a huge potential to meet the energy demands in the near future as well as over the long time. So hydrogen. So by using solar energy, we can produce hydrogen. Hydrogen, as we all know, is one of the potential energy carriers, and it has a very high energy density and low volumetric density compared to the other hydrocarbon fuels. And hydrogen can be produced from a variety of sources, including water, fossil fuels, or biomass. And by utilizing renewable energy, we can generate clean and green hydrogen, which is really interesting because it's gonna support our world's renewable energy transition as well as the net zero emission goals. What we can do once we have a hydrogen, we can store hydrogen, and later when we need, we can put them in the fuel cell to get the electricity when there is a need. So I believe the hydrogen is one of the major energy carrier to address our future energy crisis. So there are different sustainable routes to produce solar hydrogen. These are the three major technologies. So one is the photocatalysis and photovoltaic coupled electrolysis process and photoelectrocatalysis process. I'm not going to tell them detail now, but I will explain them in the coming slides. I just want to show here, these are the three major technologies that we have been using to convert solar energy into hydrogen. So before going to see the solar hydrogen production, we need to understand what is natural photosynthesis, because the artificial water spreading reaction mimics the natural photosynthesis process. In case of natural photosynthesis, as we all know, the plant can convert carbon dioxide, water into sugar and oxygen. Likewise, in case of artificial photosynthesis, which is nothing but a water spreading reactions, the semiconductor photocatalyst, which can convert water into hydrogen and oxygen in the presence of sunlight. This is basically converting solar energy into hydrogen and oxygen. This reaction is the thermodynamically uphill process, which requires a chemical energy of around 237 kilojoule per mole. So the thermodynamical potential required for water splitting reaction is 1.23 volt. So we need to have a material which can deliver potential over than 1.23 volt to proceed these reactions. So how this reaction happens by using semiconductor, this is basically an interface reaction which happens at the semiconductor in the electrolyte interface. This is the five-step process. You see, this is the semiconductor. So the semiconductor absorbs light energy. Basically, when the semiconductor absorbs light energy, it excites the charge carriers from valence band to the conduction band. Basically, the electrons leaves from valence band to the conduction band. And then once it reaches the conduction band, it tends to move to the interface where the carrier separation happens. And then these carriers involved in the catalysis process. In case of electrons involved in the reduction reactions, whereas in the photogenerator holes involved in the oxidation reaction. Based on the application, you will get the products that's what you want to produce. As I mentioned earlier, these are various different types of solar water splitting system, and starts with photocatalysis and photoelectrochemical systems, and then photovoltaic powered electrolysis system. What is photocatalysis system? The photocatalysis is nothing but semiconductor particles are dispersed in the water. So when you radiate the semiconductor with the light, again, as I mentioned in the previous slide, it excites the charge carriers. And then once the charge carriers are excited, for example, the electron in the conduction band moves towards the hydrogen evolution sites, where it reduce protons to hydrogen, whereas the holes moves towards the oxygen evolution side. It involves in the water oxidation reaction, for example, converting water into oxygen. So what we need to find in case of photocatalysis, you need to pick a right photocatalyst materials that has a band gap more than 1.23 electron volt, so that it can absorb the light energy to facilitate this reaction. In addition to band gap, there is one more thing that we have to we need to be careful of choosing the band edges. So you see, this is the water redox oxidation and reduction potential scale. So in case of, if you want to produce hydrogen, the conduction band, it should be more negative than the water reduction potential, so that it's easy to produce hydrogen. And the other way, the valence band, it should be more positive than the water oxidation potential, where you can get better oxygen evolution reaction. The second one is the photoelectrochemical reaction. That's what I'm gonna present in this presentation. So here, the photoelectrochemical, it's nothing but it combines the process of both photocatalysis and electrochemical reaction in a single cell. For example, this is the example of photoanode and photocathode. In most of the cases, you have either photoanode or photocathode. The other side, you have a dark electrodes. So where you have the reaction on the surface, when you illuminate light, and the photo absorber absorbs the light energy, again similar to the photocatalysis, and then the carriers involved in the catalysis process to produce different products. The last one is the photovoltaic powered electrochemical system. This is more straightforward approach, where you just power the electrochemical cell with the photovoltaic cell. This is basically powering the electrochemical system with different electricity. But instead of direct electricity, we can use photovoltaic cell that can utilize the solar energy to drive the reaction. Here you can see the anode and cathode is connected to the power supply. Here you can, let's assume it's a solar energy. So from the solar energy, the reaction is happening on anode and cathode side. So why PEC system compared to photocatalysis or photovoltaic coupled electrolysis process? PEC system has lots of advantages compared to other systems. For example, PEC system combines the advantage of both photocatalytic and electrocatalytic process in a single cell. And also, as you can see, it combines all the function of solar hydrogen in a single unit, whereas in case of photovoltaic coupled electrolysis process, you need to put the electrolyzer outside and photovoltaic somewhere. You need to connect them externally. That makes the system more complex, as well as it increases the overall cost of the system. So in that case, a PEC combines all the components and function everything together. So that makes the system unique compared to other systems. So here is a water splitting mechanism. As I mentioned earlier, this is a semiconductor photoanode, which can be used for water oxidation reactions. So the semiconductor photoanode absorbs light energy, it excites the charge carriers, whereas the electrons involved in the water reduction reaction to produce hydrogen, whereas the holes transfer all the way to the external circuit outside, and it involves in the water oxidation reaction at the anode side to produce oxygen. This is the half reaction. You see from the anode side, the water is getting oxidized. You get oxygen, proton, and electrons. Whereas in the cathode side, you have a proton and electron combined together to form hydrogen. So the overall reaction looks like converting water into oxygen and hydrogen. So based on the type of semiconductor, we can use the photoelectrode either as a photoanode or photocathode. So P-type material are usually used as a photoanode, which is used for hydrogen evolution, whereas the N-type material, which is used for as a photoanode for oxygen evolution reaction. So this is the band structure of P-type photocathode materials, where you can see when P-type semiconductor comes in contact with the electrolyte, the downward band bending happens because of this potential barrier between the electrolyte and the semiconductor system. So in that case, the electron can easily flow from conduction band to the electrolyte interface to do the water reduction reaction, where you will get hydrogen. Whereas the hole cannot move here because the potential barrier is really high. So the holes travel all the way to the external circuit, and it comes to the anode, and it involves in the water oxidation reaction to produce oxygen. So the photocathode can be used as a hydrogen evolution materials, whereas the photoanode can be used as a oxygen evolution materials. This is N-type photoanode material, where I mentioned in the previous slide. So here we used a semiconductor, P-type semiconductor as a photoanode, where you see when the semiconductor comes in contact with the electrolyte, its upward band bending happen, which is opposite to the P-type material. In that case, the electron cannot be transferred to the electrolyte because of the high potential barrier, whereas the hole can easily migrate because of low energy barrier. It involves in the water oxidation reaction and produce O2, whereas the electron travels all the way to the external circuit and it reaches the cathode side and it involves in the water reduction reaction produce hydrogen. Here is the net reaction. Looks like you will get water, you'll get hydrogen and of O2. So this is the tandem structure. We can call it as a photoanode and photocathode system in a single system. So how it looks like, you have an N-type semiconductor as a photoanode and P-type semiconductor as a photocathode, where it absorbs light energy. So the holes, in case of P-type N-type semiconductor, the holes reacts with the water, it produces O2, whereas in case of P-type semiconductor, the electrons involved in the water reduction takes basically converting this proton to hydrogen, and you will get hydrogen as a product. These are the different types of PEC water splitting reaction, which I have mentioned earlier, and use as a photoanode and metal cathode, and the second one would be like photocathode and metal anode, and again you have a photoanode and photocathode together in a single system. In terms of efficiency consideration, so solar energy conversion efficiency for photocatalysis, electrocatalysis, so mainly depends on the current density, basically because the chemical potential is fixed here. As we all know, 1.23 volt is the standard thermodynamic potential required to split water to hydrogen and oxygen. So that is fixed, and the light intensity, it depends on the illumination, and the only variable factor here is the current density. If you can able to generate more current density, of course, you can get more hydrogen here. The only variable in the efficiency is the rate of production of hydrogen, which is nothing but the current density. So what are the material challenges in PEC systems? So when we are looking for a potential materials, we need to look at the three important parameters. These are all here. For example, the first one is the band gap. As I mentioned earlier, the band gap should be slightly higher than 1.23 electron volt, so that it can promote the water splitting reaction, but it should not go over 2.2 electron volt. In that case, it started absorbing more UV region rather than absorbing the visible region. So we need to carefully choose the material that has a right band gap to promote this reaction. And the second one is the durability, because water splitting reaction is the harsh reactions. So the photoelectrodes tend to degrade so quickly, so it loses its performance. In that case, the semiconductor must be stable in aqueous electrolyte. And the third should be the band edges. So as I mentioned earlier, the band edges in case of conduction band, it should be more negative than the water reduction potential. And the valence band should be more positive than the water oxidation potential. Then you will have a better water splitting reaction. So in that case, all must be satisfied simultaneously in order to achieve better PEC performance. So these are all the wide range of semiconducting materials have been used for PEC water splitting applications. And as you can see, it starts from metal oxides, metal sulfides, and metal selenides, metal nitrides, and silicon, some 3,5 based material like indium phosphate and gallium arsenide. So based on the type of their material, we can use them as either as a photoanode or photocathode. So N-type material can be used as a photoanode, and P-type material can be used as a photocathode. So we need to look three main characteristics, particularly when you're choosing the photoelectrode materials. Again, the suitable band gap energy, and in most of the photoelectrode, the charge recombination is the major problem. But once it excites the charge carriers, because of the very less lifetime, the carriers tends to recombine so quickly. In that case, we will lose the performance. So that once it get excited, the charge carrier should be separated and transported at the interface to involve in the reaction. And then the last one is it should have a better catalytic activity and as well as stability in the aqueous environment. So these are some of the most studied metal oxide semiconductors. So for example, iron oxide, tungsten oxide, titanium dioxide, and zinc oxide. So these are some of the examples from the literature where they have used as a photoelectrodes for water splitting reactions. And the Fe2O3 has been widely used because of its excellent band gap for water oxidation reaction. And you see that different nanostructures have been developed, okay, from bulk to nanoparticles, nanotubes, nanosheets of different structures that can help to improve the light absorption ability of the photoelectrode as well as the overall performance. Here is another example of PT doped iron oxide nanostructures where when they dope PT with this iron oxide, you can see the better performance compared to the bad system. See that there is an enhancement in the current density, for example, from 2 milliamps per centimeter square to up to 7 milliamps. So in addition to materials, there are other things that are really affecting the performance of PEC systems. And for example, there are several strategies have been implemented to enhance the overall PEC performance. The first one is enhancing the light harvesting ability of photoelectrode through microstructure and nanostructures. And when we enhance the light harvesting ability of photoelectrode, of course, you can increase the photon to electron conversion efficiency that can really help you to improve the overall PEC performance. And the second one is the band structure engineering. As I mentioned earlier, when you tune the band structure, and you can really improve the charge carrier separations that can help to enhance the PEC performance. In that case, we can form a junction, like forming construction of homojunction, like forming a junction with the same materials, or forming a junction with the two different materials that forms a heterojunction that can really help to increase the charge carrier separations. And the third one is the protection layer. Again, the protection layer is really important to avoid the photocorrosion or the degradation of photoelectrode during water splitting reaction. The another one is the co-catalyst integration that will really help you to enhance the catalysis reaction on the surface of the photoelectrode, because most of the photoelectrodes are very good photo absorber, but really a poor catalyst. In that case, we need a co-catalyst. Co-catalyst is nothing but it's an electrocatalyst, where we can directly use that catalyst with the photoelectrode to drive the reaction. So I'll just go through one by one with some examples. So here is an example of enhancing light harvesting ability through microstructure and nanostructure. Then you have different nanostructure and microstructures of, for example, like from bulk to different structure like nanotubes, nanorods, and nanoparticle, nanosphere, that can really help to improve the light absorption ability of the photoelectrode. Basically, that will help you to reduce or shorten the carrier diffusion length so that you can avoid the charge carrier recombination. That will help you to improve the charge carrier separation and achieve better PEC performance. Here is an example from the literature. So you see they fabricated nanocone bismuth vanadate as a photoanode material, but compared to the flat, the nanocone materials has better absorption, as you can see here. And in case of flat, the absorption started decreasing after 500 nanometer, whereas in case of nanocone, it shows excellent absorption all over the visible region. That means that once you get that light, it has a multiple reflection within this core structure that improve the overall absorption of the photoelectrodes. And in terms of performance, you see with the flat surface, it has around 3 milliamps per centimeter square, whereas the nanocone has close to more than 6 milliamps current density. That shows the ability of the different nanostructure, how it improves the overall performance of the PEC device. And again, there is another example of quantum dots modified ZNO micron nanowire structures. The array of quantum dots on the surface of zinc oxide helps to increase the light harvesting capability of photoelectrode, and as well as it increase the charge carrier separation. Here is the band structure. You see the electrons are moves from CDSA to CDS and then to ZN1, then to silicon, whereas the holes moves all the way to CDS and it involves in the water oxidation reactions. Like microstructure, there are nanostructures. People have developed different nanostructured photoelectrodes that can again help to improve the light absorption ability of the photoelectrode, as well as it shows better charge carrier separation. As you can see, this is the different nanostructure. They got a TiO2 on ZN1 nanowires, whereas here some rhodium chromium catalyst on gallium nitride nanowire device. So overall, what I'm trying to conclude here is by tuning the nanostructure of and microstructure of photoelectrodes can help to improve the overall absorption of the photoelectrode, that can really help us to achieve better PEC performance. So this is one of our previous work at KAUST, where our group has developed some texturing surface of silicon photoelectrodes, where you have this texturing surface help to increase the internal reflections of the photons that really enhance the overall absorption of the photoelectrodes, that has a better PEC performance. So the second one is the band structure engineering. And so the band structure engineering is one of the strategy to improve the charge carrier separation between the photoelectrodes. And so there are different heterostructures. For example, in type 1 heterostructures, you have a semiconductor A and semiconductor B. So based on the alignment, only the electrons and holes moves only from one semiconductor to the another, not in the opposite direction. In that case, we can call it as a type 1 semiconductor. Here you can see the electrons moves from A to B. The holes moves from A to B. Again, there is no electrons or hole flow in opposite direction. So because of the mismatch in the alignment of the band levels. Here, the second one is the type 2 heterostructure, where you can see the electron and the charge carrier flow between the photoelectrode from A to B and vice versa from B to A. The third one is the type 3 heterostructure, where you have two separate semiconductors. Just it absorbs light and it involves in the individual reaction process. So this is an example of indium sulfide and indium oxide based photoelectrode, where the electron moves from indium sulfide to indium oxide. The holes moves in opposite direction from here, indium oxide to indium sulfide, that involves, whereas here the electron involves in the water reduction reaction, this holes involves in the water oxidation reaction. So again, this is one of our group previous work at KAUST, where they developed amorphous and crystalline silicon based heterojunction photoelectrode. When they form this kind of heterojunction, it's very interesting to see that these photoelectrodes can be used as photoanode and photocathode by just simply changing the catalyst. When they change the oxygen evolution, when they put the oxygen evolution catalyst on the front side of photoelectrodes, it works as a photoanode, whereas when they coat platinum as a water reduction catalyst on the rear side of the photoelectrode, it works as a photocathode. So by having this kind of unique structure, you can simply tune the same photoelectrode as a photoanode or photocathode by simply switching the right catalyst, either front side or back side, so that can be used as a dual photoelectrodes for two different applications. Again, there is another example of gallium nitride nanowires with silicon heterojunction photoelectrodes, where you see when they form the heterojunction with the silicon, the performance is really improved a lot. Example, in case of just without gallium nitride nanowires, they are only close to say like 5 milliamps current, and after it forms a junction, and the current density is really improved, and also the onset potential is reduced a lot. that means like when you form a junction of two different material that really absorbs to different region of light, and as well as it improves the charge carrier separation to facilitate better PEC performance. So the another thing is the surface protection layers, and the stability of photoelectrode under harsh reaction condition remains a major challenge in PEC. So during the photoelectrochemical reaction, the photoelectrodes tends to degrade so quickly. In that case, we need a protection layer. The protection layer is nothing but a very thin layer of metals or metal oxides can be coated over the surface of photoelectrode, which can prevent the degradation of photoelectrode, as well as it also enhances the charge carrier separation at the interface, and so that we can improve the overall stability of the photoelectrode. Here is an example of TiO2 protected silicon, and this is unprotected silicon. So the unprotected silicon you see degrades so quickly, whereas the TiO2 protected silicon so somehow stable structure. So there's another example where they used TiO2. They just coated a thin layer of TiO2 on the surface of P plus N silicon photoelectrode. So when they coated a thin layer of TiO2, the stability increased a lot. That you see, this device can last up to close to 2,500 hours of water spreading reaction, which is good. So this is one of our work that we did at KAUST. So this is a SAPIC funded project where I was also involved, a part of this project. The ultimate aim of this project was to use a triple junction, which is indium gallium phosphide, indium gallium arsenide, germanium photoanode for water spreading reaction. But during this project, we found something interesting when we were doing this work. So what happened when we just coated PT, that means without any protection layer, on the rear side, and we used this as a photoanode for water spreading reactions. So you see here during the water spreading reaction, we can see the stable hydrogen production as well as stable current density. But when we were measuring oxygen, there is no oxygen production at all, and it's also not maintaining the H2O to stoichiometry ratio. Then we realized that this is not a water spreading reaction. Something is happening, because instead of splitting the water, the semiconductor itself degrades and it produces the current density, but it's not a water splitting reaction. So to further evaluate that, we coated 40 nanometer of ALD TiO2 on the protected, on triple junction photoanode. Again, we did the same experiment. So we again got this stable hydrogen production as well as current density. But when we started measuring oxygen, up to 1 hour, the oxygen was stable, and again it lost. That means that even with the production layer, it's not stable. So what we did finally, we put a TI foil, it's a thick foil, few micron thickness foil, and then coated PT on top of it. In that case, we got a stable hydrogen, as well as when we started measuring oxygen, the oxygen also stable, and it also maintains the stoichiometry ratio of 2:1, which indicates a true water spreading reaction. What I'm trying to say here is, like, even if the production layer, people think that the photoelectrodes are stable to perform the reaction, but it's not. But you need to really monitor the oxygen evolution reaction parallelly to understand this is really a water spreading reaction. Otherwise, this is just a photocorrosion. That means the photoelectrodes undergoes degradation, the photooxidation and photocorrosion will happen. In that case, you will see the current density stable, but it's not from the water spreading reaction. That's just coming from the photocorrosion of your photoelectrodes. So the next one is the co-catalyst integration. Co-catalyst is one of the important component in PEC water spreading reactions. For example, in case of silicon semiconductor is a very good photo absorber, but it's a really a poor catalyst for water spreading reaction or for any other reaction. There are several semiconductor material which is a very good photo absorber, but it's not a good catalyst to promote the reaction. In that case, we need an electrocatalyst. In case of PEC, we can call it as co-catalyst. So because along with the photoelectrode, it facilitates the reactions. So what happened? Why we need a co-catalyst? The co-catalyst is really important because it can help you to accelerate the surface reaction, because the water spreading is on surface reaction, and it also reduces the reaction over potential and improve the charge transfer at the photoelectrode and the co-catalyst interface, so that you can get a better PEC performance. And based on the co-catalyst, you can really alter the intermediates to get a specific products that you are looking for. For example, you can use for water splitting reaction for other application. For in case of CO2 conversion, you can use as a co-catalyst to control the products. For example, to CO2 to methanol or ethanol or ethylene, you can control that what kind of products you want. So in that case, that can really help you to achieve a specific products, and it enhances the overall conversion efficiency and the reaction selectivity. So this is one of my previous work at back at COUS, so where I developed ruthenium single atom incorporated mixin as a co-catalyst material for photoelectrochemical hydrogen production reaction. I tried a wide range of single atom, but ruthenium was the best one, which gave us a better performance. And we thoroughly characterized our materials using various techniques. Here you can see the dark field scanning transmission electron microscopy image, where you can see the bright dots. It indicates the presence of the ruthenium single atom as well as the cluster. I forgot to put the scale, which is 1 nanometer. Yeah. So we have also done the synchrotron measurement, as X-ray absorption measurement, to confirm the you have a ruthenium single atom metal, which clearly shows it's compared with other RU foil and RU oxide. It's something different, which because we are trying to coordinate this ruthenium with nitrogen sulfur. So we form the coordinated interacted metal single atom with mixin support. First, we evaluated the electrochemical performance, and it shows better performance. And this is our catalyst performance compared to the tough system with other from the literature. And then we integrated this catalyst. You see, this is our catalyst schematic image. Integrated this catalyst with the P plus N. PN plus silicon photoelectrodes, and it shows better PEC performance in terms of current density as well as the onset potential. And this is the comparison that we made with the existing literature reports. This is another project that we used MOS as a co-catalyst for photoelectrochemical hydrogen production. This is with the silicon heterojunction. This is the bare cell. See, the performance is really low and the over potential is really high. But when we couple MOS to it, then the over potential is really decreased a lot and the current density increased. So this is our another project where we used a gold coupled graphitic carbon nitrate as co-catalyst, but this is not for hydrogen production. This is for nitrogen reduction to ammonia synthesis. So what I'm trying to say here is, while choosing the catalyst material that can really help you to do various kind of reactions, we use the same photocathode device, but when we change these catalysts, they can be able to change the reactions. So for example, here nitrogen to ammonia synthesis, and we got this work published in 2021, so which has a very good, showed a very really good nitrogen to ammonia performance. So there is a bias-free PEC system, basically with a high efficiency device. The photoelectrode material that can be capable of producing photovoltage more than the water spreading reaction. We can use those devices for water splitting reaction without applying any external bias. We can call it as bias-free or zero bias PEC system. There are three different configurations. The first one is the wire connector configuration, where you have a photoanode and photocathodes are connected optically and electrically in series with an external wire, so that you have a water oxidation reaction at the photoanode and water reduction reaction at the photocathode. The second one is the wireless configuration, where you have only the catalyst is separated from the light absorber, but connected by an internal electrical circuit. That means you have two parallel photoelectrodes, and the photoelectrodes are decoupled, but only the photoelectrodes are in contact with the catalyst. In that case, you don't have any wire. You just put the device in the water, just shine light, you will get the water splitting reaction happen, and you can see the bubbles coming out. The third one is the monolithic configuration, where you put everything on like a stack, you can together in a single cell. The catalyst materials and light absorb, but it's called a fully integrated device. In that case, you can do the reaction with on the device, and you can perform PEC reactions. This is an example of wire connector configuration from literature, where they used antimony selenide photocathode and BA for photoanodes, where they wired two different devices and they can able to achieve a solar hydrogen efficiency of 1.5%. And this is one of our previous project where we had a collaboration with Professor Stefan at Gauss Solar Center. They are expert in fabricating a fully textured NIP perovskite silicon tandem device. Here is the device that the architecture, the device that they made. So the beauty of perovskite silicon tandem cell is can able to produce high photovoltage, which is close to 1.8 volt, whereas in case of water splitting reaction, the thermodynamic potential is 1.23 volt. So when we have such high voltage, you can demonstrate this kind of device for bias-free or water splitting reaction. That's what the idea comes in. So I just took their cell and I fabricated the cell with the platinum TI foil as a catalyst on the rear side, and we demonstrated this device for photoelectrochemical water splitting without any bias. So in that case, we were able to achieve solar to hydrogen efficiency of 14.12%. So this is the device configuration. You see that I have used as a horizontal illumination. On the rear side, you will get the electron, whereas the front side, you will get the holes. So the reaction, the electrons reaches the platinum nickel catalyst side, that it involves in the hydrogen evolution reaction. I just show you here, this is the photoelectrode that I made. So here you see the hydrogen comes out on the rear side of the photoelectrodes, just shining the light without applying any bias to the system. So this is the wireless configuration. As I mentioned earlier, you don't have any wires here. This is from the recent literature where they used a hybrid perovskite-based wireless integrated device. These are the devices you see. So for example, this is a photoanode and this is a photocathode. These two devices are separated, whereas their catalysts are connected to the photoelectrode. In that case, you just shine light, you will get hydrogen comes out from one direction, one side. That means from photocathode side, the oxygen comes from the photoanode side. So this is the monolithic configuration. You put everything together on a single cell, the catalyst, everything. So just shine light, you will get the bias-free water splitting reactions. So this is the summary of bias-free solar water splitting system of different configurations, wired configuration where they use different photoanode material and photocathode material. This is the wireless PEC water splitting, and this is a monolithic. So far, the maximum efficiency, solar to hydrogen efficiency of around close to 20% has been achieved for the stability of 20 hours. So based on the recent literature, what we found is the future device would be something, the membrane embedded monolithic PEC device. In addition to the issues what we have seen so far, there are other problems in case of ion diffusion between the electrodes. In that case, putting a membrane between the electrode can help us to transfer the ions quickly, which can improve the overall performance. In addition to that, they are proposing that having a device that can maximize the light absorption of both photoanode and photocathode, so that you can overall improve the performance. In that case, when we want to put the membrane, we need to understand the three characteristics. For example, how we are going to position this membrane without affecting the performance or without affecting the incoming light. And the optical transparency of the membrane should be a key factor. Otherwise, it blocks the lights from one side to another side. It does not allow the light to pass through to reach the other electrodes. And again, the nano or micro structuring of the absorbing layer. So overall, so we need to think about in different directions how we are going to make this kind of device to improve the overall photoelectrochemical performance. So the conclusions, the PEC has a huge potential for scalability because of it's a very efficient device that you can used for solar hydrogen production applications. What we need to think about is we need to find a new materials. For example, making stable material with better efficiency. Again, the vice versa, having efficient materials should be more stable. Basically discovering new material that are intrinsically stable and highly efficient. In addition to that, we need to prioritize the properties to search for different things like band gap, how the stability, and how we are going to get the band alignment with those for water that aligned with the redox reaction potential, and choosing the right co-catalyst material. So it needs the combination of theory, synthesis, and characterization group to work together to achieve a fundamental PEC goals. So to make the PEC cells more competitive, their solar hydrogen should go above 10% and the life longer than 10 years. And this really need a material development and with the scalability to demonstrate the photoelectrochemical cell for practical solar hydrogen production. And in addition to that, a low cost photoelectrochemical tandem cells that uses the earth abundant semiconductors, or basically low cost semiconductor material, as well as the first transition metal co-catalyst, has the greatest potential to achieve a sustainable future for our renewable energy transition, and that will really help us to achieve future net zero goals with zero carbon emissions. So this is the overall presentation today. So I take this opportunity to thank my previous organization, King Abdullah University of Science and Technology, KAUST, where I did my most of this for electrochemical research. And then I would like to thank my previous fellowship organization from Ibadullah Hispana under Energy for Future Fellowship with the Marie Curie Coffin program at the University of Strathclyde. And I take this opportunity to thank RGU for this wonderful opportunity to share some of my research in this webinar. Thank you very much. I'll be happy to take a question.
Thank you very much, Vinod, for a very interesting presentation. So is there any question we have? Yes. Yeah, we have one hands up. Yeah, go ahead. Hello.
Hi, Ismail Jalisi. Thank you very much for an excellent presentation. How close is this to commercialization?
It's a good question. So there is a paper recently published. I haven't put that one here. So the photoelectrochemical cell can be used with the concentrated solar light illumination, where you can really scale up the device, where they can able to achieve up to 2 kilowatt of hydrogen with the solar hydrogen of 20%. So again, as I mentioned in the outlook slides, you need to really maintain the efficiency of solar hydrogen 10%. Again, you need to maintain the stability for 10 years. That's really challenging, but there are few groups that they are really doing work towards scalability. Probably it takes a lot of efforts in a different way, like materials and the device point of perspective. We need to work a lot to bring this system towards more commercialization. So.
Thank you.
Thanks very much. Is there any other question? It seems like we have dried up the questions. Before we go, I would like to just kind of ask a very simple, straightforward question and get your comments on it. So if you want to kind of increase area and reduce the over potential, at the same time, the other challenge is to reduce the cost of the material. Can you hear me?
Sorry, Ketan, I missed your point. Can you repeat the question, please?
Okay, yeah. So it's kind of more of a comment rather question. I would stick on this idea, like as far as I know on this area, and especially a solar in this water splitting, the the main aim is to increase the area with reducing the O potential, and same time not using the expensive and very critical materials. So where we are in that context, are we trying to find iron oxide or something which is cheaper? At the same time, can we find a compromise between the material wastage at the same time, not using very expensive material and, kind of sacrificing a bit of efficiency while increasing the area of it, because you need a production at a higher scale. Probably you need a large area with the low over potential.
It's a good question, Ketan. So yeah, as we all know, platinum and other noble metals are very good for this kind of reactions. But the problem again, it's a really cost, and as well as it's a scarcity. Like you don't find it easily, and it's really really expensive. So in that case, there are other materials. For example, like bismuth vanadate. Let's say it's a very good photo anode material, which has a very good photo voltage. The people are using as a photo anode in a large scale, where that has a huge potential, like the hematite photo anode, which is very cheap. Again, you have to trade off between the performance as well as the materials cost. But no materials can compete with the platinum. That's the problem.
I know.
So that's what I said. Like, if we need a new materials, or we have to really tune the material that can outperform the existing noble metal catalysts. That's a big question. So people are trying to use different materials, like I said, bismuth vanadate and hematite and titanium dioxide. But again, somehow the performance is not at level, right? So that's what the actual research, like people are trying to find new materials to do that.
So do you think in material terms, are we going into the area where we have a complex metal oxides, where you have more than one or two metal combined with sulfide, oxide, or nitride, in kind of finding new material which would reduce the cost as well as kind of bringing in the benefit of the efficiency?
Yeah, that's a good idea. But how this dopant going to help us to achieve better performance, and what kind of interaction, the chemical bonding, how it's gonna tune the band edges to. Sometimes when we dope high band gap material, it affects the overall light absorption ability of the photoelectrode. In that case, we have to be careful about the intrinsic properties of any material that we want to put in. But that's a good idea that, like a cheap material we will try and we can use, and how it interacts with the photoelectrode materials, how we tune the overall optical properties and electronic properties of the system. And then that will help us to reach up to certain level to close to the performance of any noble metal based systems.
Oh, thank you very much. That's an elegant presentation. We learned today a lot of stuff, and it's thankful for your sharing your experience and past research, as well as bringing in some perspective from the literature. So thanks very much, Dr. Ramalingam. And I think with that, I want to announce one more thing before we go. So the next All Things Hydrogen webinar will be on the 29th of February, starting from 10 a.m. And it will be like 1.5 hours, delivered by Dr. Sudhagar Pichimuthu from Heriot-Watt University, and he will be discussing the green hydrogen generation from photo and electrochemical technology. So as usual, we will share the link with everybody, and everybody who is listening can pass on this message to others as well who are interested all things hydrogen and research in area. Thank you very much.
Thank you.